The second type of improper integral that you are going to come across is when your integrand is discontinuous. So most of what we've talked about so far, as far as calculus is concerned with definite integrals, is you've had a continuous integral. So what happens if you don't have one? Like if you wanted to find the integral of 1 over x, let's just say, from like -1 to 1. Well, can you actually add up the area between the function and the x-axis there? And what happens when we have a discontinuity? Like there's all sorts of really interesting things that we need to look at when this is concerned. So that's what we're going to be doing. If you know that the function is continuous everywhere but at that endpoint, then you can use limits to say, okay, as t goes to that endpoint from the left-hand side, what's going on with this limit? Same thing if it was the lower bound is the issue, then we would just change it. Take the limit as you approach that lower bound from the right-hand side and integrate. Again, convergence, divergence is still the same as before. And if you end up having continuous over a to b except for one point, then you could split this up. So in our example right here, like at x equals 0 is where my point of discontinuity is. So I could set that up to go from a to 0 and then 0 to b, and then you'd have to do this on each side of that discontinuity. All right, so let's look here at example 1. In example 1, we have the integral from 0 to 4 of 4 minus x inside a square root in the denominator of our integrand. So if I plug in 0, I get 1 over square root of 4. That's not where my discontinuity is going on. But if I plug in 4, 1 over 4 minus 4 gives me 0. And so I must actually have a vertical asymptote, just with normal function evaluation, knowing that the 0 here is a number over 0, and so that discontinuity is a vertical asymptote at 4. So because I have that discontinuity on the upper bound, that's what I'm going to let t be. So I'm going to say take the limit as t goes to 4 from the left of the integral from 0 to t of 1 over the square root of 4 minus x dx. Now let's do a little mini u sub on this one. So if u is this inside piece, then du is negative dx. And so I would be looking at the integral of 1 over square root of u and negative with du. That would be negative u to the negative 1/2. And so if I took the antiderivative of that, I would have u to the positive 1/2. Dividing by half is the same as multiplying by 2. Let's go back over here. So this is going to be the limit as t goes to 4 from the left of negative 2 times the square root of 4 minus x, and that's from x equals 0 to t. Let's go ahead and plug in. So negative 2 square root, or I can even take the negative 2. Let's do that. Let's take the negative 2 out here and not worry about that for a minute. All right, 4 minus t minus, when I plug in 0, square root of 4. So negative 2. What happens when t goes to 4 from the left here? So I'm plugging in numbers like 3, and then 3.5, and then 3.9, and so on and so forth. So this is going to end up going to 0 because I'm going to have numbers that approach 0 from the right-hand side. So I'm going to end up having 0 minus square root of 4 is 2, negative 2 and negative 2. That full area is going to be 4. All right, let's look at another example here. So we are going to integrate from 1 to 5, a very similar function. Now in this case, notice that my integrand is discontinuous at 1, So I'm going to let this be the limit as t goes to 1 from the right-hand side, because my interval, right, goes from 1 to 5. So now I'm approaching 1 from the right-hand side. T to 5, 1 over square root of x minus 1 dx. Very similar integral process if I let u be this inside piece. The only difference is I'm going to end up having a positive 2. So I'm going to take that out here, and I'm left with square root of x minus 1 from t to 5. So 2 times the limit as t goes to 1 from the right. I plug in 5 and I get square root of 4 minus t minus 1. And now we're plugging in numbers bigger than 1. So I'm plugging in 2, then I'm plugging in 1.5, then I'm plugging in 1.1, and then 1.01 all into this t. Well, that means this is going to go to 0, and I again get 2 times the square root of 4, which is 2. And so I actually get 4 again. And if you notice, the bounds were pretty similar. And so my change in x, change in y over time ends up being the same. What I mean by that is like 1 to 5 here, and then here I went 0 to 4. So like that x bound is the same. And then I do have similar functions. So it would be interesting to look at a graph of these and how they are very similar, how kind of like translations work, and those things would be an interesting thing to look at. All right, let's look at one more example. This is going to be with a discontinuity on the inside. So integral from -1 to 1 of 1 over x cubed dx. So 1 over x cubed is going to be like 1 over x, and then from -1 to 1. So 0 is my discontinuity. So let's break this up. -1 to 0 plus 0 to 1. Okay, on this first one here, I'm going to say the limit as t goes to 0 from the left, integral from -1 to t of 1 over x cubed dx. And then I'm going to choose t again, but I'm going to 0 from the right. And I'm going to evaluate these actually separately from here on out, and then I'm going to plug them back in with the sum. So on this side here, I have x cubed, that's x to the -3. So limit as t goes to 0 from the left of x to the -2 divided by -2, so -1/2 from -1 to t. So limit as t goes to 0 from the left of -1/2, 1 over t squared minus 1 over -1. Now, when I go to plug in 0 here, I end up getting 1 over something that gets really, 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 really small. And so this actually gets really, 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 really big. So I have a divergent side over here. This piece again, right here, as t gets really, 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 really small, that whole fraction gets really, 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 really big. I can't add up that area. So in this graph, as I'm approaching -infinity, or as x goes to 0 from the left, or t goes to 0 from the left, however you want to think about it, and I'm approaching -infinity down here, I'm not going to be able to add up the whole thing. So it doesn't even matter if this side over here converges or diverges. Remember, once I get something that diverges, we're out. So this is a divergent improper integral. I cannot find the area here. Now, that doesn't mean that's true for all the times that we split up on a bound here. This is just one example though of when you do have a divergent side, what we can do with that and how we can, or whether we cannot, I guess, add up everything. And so it's like, we can't do that here. So we just say that it diverges, and then that's going to be our answer. We cannot add up all of that area.